From the beautiful studios of Way Happy, it's a slightly stuffy Mr. Meyer and 3.1 exponential and logistic functions. Now, exponential functions are one you've seen before, growth and decay, right? So they take the form, not power functions. Remember, we just finished up a little bit of power functions? And the thing about power functions was you had x to some power. Well, an exponential is when you have some number to the x power. That's the difference between an exponential function and a power function. So whatever that number is, that base right there, if that base is bigger than 1, then we call it a growth graph, and they grow away from their asymptote. They have this asymptote, you may recall, right here at y equals 0, and they grow away from it as you read from left to right. Now, if that base is between 0 and 1, then we are talking about a decay function, and decay is kind of decay down to the asymptote, going from left to right. So you'll see it slowly decay. So the base is really what's important in giving you an idea of how this graph works. But guess what? All the translations are the same and everything else is the same. We still move it left, right, up, down. It doesn't really matter. So if I'm going to go ahead and sketch this graph, and one thing I should point out too real quick is this point right here, that the parent functions will go through that point 0a, where a is that leading number. And it'll make more sense if you just made an XY chart anyway. So let me show you a graph. So here's my graph paper. And I might notice something about this graph. I might notice that there's my A value, there's my B, and I might notice that it's actually shifted right 2 units. Good to know. So if you want to know what the parent function looked like, right? If you want to just scribble out the right 2, if you wanted to know what that was, well, you could. Here, I'll make an XY chart. And the 2 best points to plug in would be when x is 0. And so if x is 0, you get 2 to the 0 power is 1, and 1 times 3 is 3. And that's why you always go through the point 0a. And then you might want to test the point 1 comma something. So 1 comma something would be 2 times 3 is 6. So the original non-shifted graph would have its asymptote right here. And then it would go through the point 0.3 and through the point 1.6. 3, 4, 5, 6. So it would go like that. So again, it's going to start here, and then it's going to go through those 2 points and out of here. Now just move each point right 2 units. It's a right 2 shift. So why don't we just take all of our points and move them right 2? So in other words, add 2 to the x. So you'd have 2, 3, and you'd have 3, 6. And so you would have 2, 3, and you would have 3, 6. And you could see that now our graph again starts here and then goes through there. You could find the y-intercept if you want. Super good idea, right? Make x 0, and that would be, what would you get? If x was 0 on this function, you would have 3 times 2 to the negative 2. So that's what, 3 over 4? If you think about that for a minute. So it goes through 3/4. So I was a little wrong. It should have been like right through there, right? So what a horrible sketch. Nice work. Let's try this guy. Right? Notice it's flipped. The negative out front is telling me to flip it over the x-axis. I should put axis, I guess. There's my A value also. There's my B value. This is a decay graph, and it's also up 2. So here's my graph paper. If I make that, I will have my graph paper. And I will then say, all right, it's a decay graph. So usually I would think a decay goes like this, but surprise, this one's got a negative. So it's going to actually go this way, right? It's going to decay that way. Well, a lot of the cool stuff still holds true. Like before we do the up 2 shift, here is this asymptote. And then I'm going to go through the point 0a, which would be 0, negative 4, and makes sense because the negative, it's flipped. And then if you wanted to, you could plot one more point. You could make x a 1 and, whatever the heck 4 times 0.3 is. It was like 1.2. I would get another point there. So this is the non-shifted one. There's my decay graph. So if I want to move it up 2, no big deal. I'm just going to move my asymptote up 2. And again, if you wanted to, you could just plot points. know that from that asymptote now I would go through 0A, which means still down 4. 1, 2, 3, 4 be right here. Or I could have said I just moved this guy up 2. And then same thing here. This guy's got to get moved up 2. Boom. And there is my beautiful sketch of that graph. That is a decay graph, believe it or not. It is decaying down towards the horizontal asymptote. All right, what about this fancy thing called Euler's number? Euler's number is a number that shows up in a lot of things, especially in nature, things that grow continuously. So if you ever see continuous growth, or you're reading a problem and you think that it's growing continuously, it's not growing in chunks like every month or something. It's growing every millisecond. Then Euler's number, E, is a really good number to use. And just so you know, it's just a number. Like pi is 3.14. Euler's is 2.718. And it goes on a little longer. In fact, forever. And you could just think of it almost as 2.7, or think of it as 3 sometimes when I'm doing mental math. So look down here. Any exponential graph, there's an exponential, can be written in Euler's number. Usually all you'll have to do is figure out what the heck b is in the first one, how you could rewrite it as e to the k power. A little bit of algebra will get you that. But let's just talk about the sketch real quick. Look at this first one, 3e to the x. There's your a, there's your b. So b is 2.7. That's a growth graph, so I'm expecting an asymptote like this, and it's going to go through 0, 3, and it's going to be a growth graph. So it's going to look something like that. Done. You could plot another point if you want. No big deal. Look at this guy, the one next to it. I have 5. That's your A. You have Euler's number, which, ooh, be careful. Remember, that's a 3, but it's a 3. I'm going to rewrite this for a minute. To the negative 2 power. Remember, if you have two exponents, you just multiply them together. Well, you can also break them apart. So think of that as 3 to the negative 2 power, or 1 over e squared is your base. Remember, e is like a 3 in my brain, so that's like a 1/9. Now, it's not quite, but it's like a 1/9. I could get away with that. And so this is a decay graph, so I know it's decay. So I'm going to go ahead and plot my asymptote right here because there was no vertical shift. And then I'm going to plot the 0.05, 1, 2, 3, 4, 5. And I'm going to draw a beautiful decay graph through there, get really close to my asymptote. There's a sketch, right? So Euler's number, just think of it as 2.7, or if you have to, 3, to make the math a little easier. And you should be able to graph anything. All right, let me ask you a question, and we'll be right back to talk about logistics. Nice work. All right, let's talk about something else. Let's talk about logistic functions. Now, they like to take populations in math and stuff like that, and they like to talk the population of Granada, and they like to say it grows exponentially, and oh my gosh, how great. But can a population really grow exponentially? I mean, yeah, at first it can, but isn't there a point where Granada would be so full that we wouldn't have room for students anymore? Like we'd be piling, 100 kids in a classroom, and that's just not possible, or thousands of kids on the quad. It's not going to work. We just don't have that much room. So that's what a logistic function says. It says, all right, I'm going to start off, you look like you're growing exponentially, but then what happens is you kind of level off at this limit to growth, because that's about all we can hold, right? So, or that's all there is in the school, or whatever. So remember back from chapter 1 that these logistic functions, they have two horizontal asymptotes, and they live in between those two asymptotes. And the cool thing about them too is, if you might look here at the equation, one of them is always y equals 0. Well, unless it's shifted up or down. The other one is y equals c. And you might notice that c is the numerator. Now, again, you might notice two equations here. Beautiful, like that. One of them uses Euler's number because, again, we might be talking about something growing continuously, while the other one maybe grows in chunks or whatever. And so I like the Euler number one, so you'll probably see me use that the most. So let's talk about what this graph looks like. So you can see down here in example 1, I got just in time the number of Granada High students that have Matador spirit, right, during the homecoming week can be modeled by this equation right there, where T is the number of days since the teacher skit. So if I want to talk about how many students, my first question, what's the initial number of spirited students at Granada? I could use that, but you have to realize that what we are using is t equals 0 because the teacher skit hadn't happened yet. So the days since the teacher skit would be 0. There's not been any days since the teacher skit. All right, then I just take my equation and I really don't have to do too much because think about it, if that t value is 0, then I have Euler's number to the 0 power, and anything to the 0 power is 1. So I have 1 times 14.5. So really, what do I have? 2096 over 1 plus 14.5, because all that other stuff turns into a 1. Beautiful. So I'll grab virtual Sheila here, and I will ask her to calculate 2096 divided by 15.5. And she will tell me there's 135 spirited students at Granada on that Thursday before the teacher skit. Well, let's move a little farther. How many students will be spirited for the freshman skit? So now the teachers have performed on Friday. The students have gotten excited and just amazed at how well the teachers have done. And now you can feel that momentum building. So Saturday, the kids are getting fired up. Sunday, they're getting fired up. Monday comes and they're going to go out and they're going to be spirited. So we're talking T is 3. And we want to know how many students we could expect to be spirited for that freshman skit. So again, I'm going to use my calculator to calculate a nice, simple 2096 over, by the way, that's the population of, I think, Granada. Kind of guessed, but we can pretend it's awesome. E to the, what do I have? Negative 0.81 times 3, and boom, holy macaroni, the teachers have fired up some kids. So the freshmen are very thankful that there are now 938 spirited students at Granada after that teacher skit got them all fired up. All right. See if you really understand logistics, though, because the cool thing about a logistic is what is the most number of spirited students possible? So where does this graph right here, where does it level off, right? Well, remember that little trick about looking at the numerator? Boom, right there. It levels off at 2096. That is the most we can ever get because that's how much we have, right? Or that's the limit that we were able to hold. But for us, that's how many students we have. So that is how many that we could possibly get. And then when will we have 1,500 spirited students? Well, not a big deal. I will take that equation and I will set it equal to 1,500, and I will have to solve it. Now, that might scare some of you. There's a couple of ways I could think of doing that. I could graph it and find the table. In fact, that's what I'll do. I'm going to put this in Y1. I'm going to turn my stat plot off because I don't want that to mess up with anything. So I'm going to put 1,500 in Y1. Remember, the left side of the equation into one thing. The right side of the equation is going to go into another. Wish I could have copied and pasted. That would have been nice. 2096 over 1 plus 14.5 second. I think it's the log, natural log button. Negative 0.81 to the x. And boom, there's my graph, right? So I'm going to go zoom. What do you think? Zoom fit, zoom 0. Let's see what. There's the 1,500, and there comes the logistic through there. Oh, gorgeous, right? And what am I going to do? I'm going to ask my calculator to find the intersection. So second, calculate the intersection, number 5. The first curve is 1,500. Yes, I'm going to hit enter. Second curve is that gross one. Yes, I'm going to hit enter. And now I'm going to move the cursor from wherever it is over to where I think the intersection is. Hit enter, and bam, there you have it. 4.4 is X, or X represented days. So 4.4 days after the teacher's skit, you shall see 1,500 spirited students, right? So that's crazy. What if we're selling stuff in Granada wear and we want to know when we have 1,500 t-shirts and we want to sell out or whatever? When should we do it? Well, let's wait 4 days. So teachers went on Friday. So Saturday, Sunday, Monday, Tuesday is 4 days. So let's wait until Wednesday and we're going to sell out. It's because everyone's going to be so excited. Let's just make sure you do still really understand these logistic graphs. What if I asked you to sketch a graph of one? Because I'd love to make you sketch. So what would you do? Well, hopefully the first thing I would see you do is this. Putting in an asymptote at 0, putting an asymptote in at 9, and you know the graph lives in between there. And now let's just figure out, make x is 0, and let's find that y-intercept. Because remember, when x is 0, you get the y-intercept. So this was, by the way, at y equals 9, and this was y equals 0. And so if I plug a 0 in there, what do I get? I get 9 over 1 plus 2, or 9 over 3, which is 3. So that's our y-intercept. 1, 2, 3. I guess I probably should have done a real one. And there's my graph. It starts off at this asymptote, and it increases the entire time to there. And that's your sketch. Why don't you try the next one? Pause the video, try it, and see what you get. Yeah, you didn't pause it. I know. What do you got? You got one asymptote right here at 0. You got one asymptote at 8. 1, 2, 3, 4, 5, 6, 7, 8. That looks so much better. There's the other asymptote. And now let me actually sketch it again. I'm going to put a 0 in for x. So that's going to be 8 plus 5. So 8/5. What the 8 plus 1, 8 over 5. Sorry, 8/5. So that's like 1.6. And so boom, there she is. So it's going to start like this. It's going to go through that point, and then it's going to level off. That's how you sketch these bad boys, right? Piece of cake. Once we do logarithms, we'll be able to solve the other way, which maybe you want to try sometime, like that problem with the 4.4 days. Have a great day. I will see you tomorrow. Keep your Granada spirit.